This is the first lecture from Chapter 14 on kinetics, or the rate of reactions, and this is just simply an introduction lecture. A couple basic definitions for you. So kinetics is the study of how fast reactions go, or the rates of chemical reactions. And the rate of reaction, jot this down, make a note of it, because we get involved in a lot of mathematical equations, and for some reason this simple definition and units tend to get lost. So the actual rate of reaction is defined as the change in concentration of a reactant or of a product, whatever you're monitoring, over the change in time. So here's kind of a summary of what the rate of a reaction. And so what would the units be for rate of a reaction? Well, concentration would be on the top, so molarity is probably the most common, and over time, so that could be seconds, minutes, but these are typical units for the rate of a reaction. So if you were to plot the concentration of a reaction over time, of course, if it's a reactant, you would expect the concentration to decrease over time, right? Because it gets used up and converted to product. And so what the rate is, change in concentration over change in time, is really the slope of a plot of concentration versus time. So just like I said, kind of make a note of that and then look back at it every now and then. A couple of clarifications on some of the symbolism we use. These square brackets that you'll see very frequently in chemistry mean concentration, specific molarity, and the rate, as I mentioned before, is a change in concentration. So it can be the change in concentration of any substance in a chemical reaction. It could be any of the products or any of the reactants. Keep in mind that if you're monitoring the rate of change of reactants, they are disappearing over time, and so that's typically designated with a negative sign. If you're monitoring the change in concentration of products over time, they are increasing, and so there is typically designated with a positive sign. Again, just kind of a reminder of the common units for rate. So it's concentration over time, so that's typically molarity per second. Remember what molarity is, it's simply moles per liter. So you might see rate expressed like this, and then in case you have forgotten from math, anything you have raised to a negative power simply means the inverse of that. So this last unit would be molarity over second, same thing. So these are the type of units. Units become very, very important in kinetics. So let's think about the rate of a reaction over a period of time. So when you first start a reaction, the rate is going to be the fastest. And over time, as product disappears, the rate will decrease. So I want you to think about that. Why might that be? That's because in the beginning, you have a lot of the reactant, so there are a lot of collisions going on, and so it goes very, very fast. As you have less and less reactant, they encounter one another less frequently, they collide less often, and therefore the entire rate slows down. Also, typically as the amount of product builds up, quite often there is a reverse reaction, and so you kind of have a forward and reverse situation going. When the overall net change of reactant and product is zero, you have reached a state we call equilibrium. Equilibrium is kind of the pinnacle of this semester of chemistry, so I try to introduce it here and there. So let's look at what I just said graphically. Let's look at another plot of concentration versus time. And remember, I said that it's actually the slope of this graph that will give you the rate. But the issue is the rate of reaction itself changes over time. So the rate in the beginning of a reaction is always quite a bit larger, in this case 0.08 molarity per second, versus, say, 10 minutes into this reaction, the rate or the slope decreases to less than half of that, 0.03. Which rate do we use? So that's an important consideration, and typically what scientists will try to do is measure the rate at the very beginning, and they call that initial reaction rate. It gets a lot more complicated measuring the rate as it proceeds. You have more substances that have formed, you have the reverse reaction is picked up, so it is much more straightforward and simple to measure the rate in the very beginning. So again, measuring the rate in the beginning is called the initial rate of reaction, but you can measure the rate anywhere along the reaction pathway. You would just simply have to draw a tangent line to wherever you were measuring the rate and then get the slope of that tangent line. So for instance, let's say I gave you this graph of concentration versus time, and I asked you to figure out the instantaneous rate at 10 minutes. You would have to draw a tangent line to the slope at 10 minutes and then measure the slope using that tangent line. So those are called instantaneous rates. So far you've seen graphs that show change in concentration of reactants over time, and we've talked about the concentration of the reactants decreasing, but rate can also be measured by monitoring the change in concentration of products. And typically, whatever is easiest to monitor. So if you have a product that turns bright red, you might likely follow the intensity of that red color. So really, whatever reactant or product is easiest to follow is the one that's monitored. So we could monitor products. What would you expect to happen to the concentration of product over time? You would, of course, expect the concentration of product to increase over time. And you'd find the rate the same way by drawing a tangent at wherever you wanted to monitor it. We can also learn information about the stoichiometric relationship between reactants and products by looking at a graph of the change in the concentration versus time. So for instance, the stoichiometry of the formation of hydrogen iodide. One hydrogen combines with one iodine molecule to make two hydrogen iodides. So if you think about the disappearance of hydrogen, for every one hydrogen that disappears, you form two hydrogen iodide. So in other words, hydrogen iodide forms 2 times faster than hydrogen disappears or than iodine disappears. And you can measure that in the rate. So assuming you measure the rate at the same amount of time for each of them, you would notice that the rate of appearance of HI is 2 times larger than the rate of disappearance of either hydrogen or iodine. And so we're going to get into something called rate laws and rate expressions, but to just kind of give you an introduction, if you were comparing the rate of hydrogen to the rate of hydrogen iodide, you would say that the rate with respect to hydrogen is 1/2 the rate with respect to hydrogen iodide. Okay, so just kind of give you a preliminary glimpse when we compare rate expressions with respect to different reactants or products. So keeping that rate expression in mind that I just showed you for hydrogen iodide, let's look at another one. It's essentially just the reverse of the one I showed you. But in general, for a balanced chemical reaction, you can determine or set the rates of reactants and products relative to each other as an equivalency by taking whatever the coefficient is and putting 1 over that coefficient. Okay? So 1 over 2 times the rate with respect to HBr, which is the change in concentration of HBr over change in time, equals, and of course there's only a 1 in front of hydrogen, so you can think of it as 1 over 1 or just leave it out. And if we were to include bromine, it would be the same thing. So that's a simple math equation, but it's used pretty frequently. So here's the generic expression. Now, this is the rate of a reaction. Again, in the next lecture, we're going to be talking about rate laws, which are different. So please understand that the rate is change in concentration over time. That's going to be different than rate laws. So if you're comparing the rate with respect to the different reactants and product, again, here's the generic formula. It's whatever the coefficient in the balanced reaction is, it's the 1 over that, times the change in the concentration over change in time. Now, remember that reactants are disappearing, growing smaller, so they have negatives, and the products have positives. They're increasing over time. And this relative relationship between the rates can be seen in a graph. So I'm hoping just glancing at this graph, you can see, for example, that nitrogen disappears, or its concentration decreases less rapidly than does the concentration of hydrogen. And if we had a quantitative scale on the y-axis, you could figure out what the factor difference is here. You can look at the balanced reaction and see that it's a factor of 3. So hydrogen disappears 3 times faster than does nitrogen. So if you were to write the relative rate expressions for all of these, and it looks like I picked a bad color to understand that, but you would, there we go, change in concentration of nitrogen over time, and hydrogen has a 3 coefficient, so probably easier to understand like this. 1 over 3 times the change in concentration of hydrogen, and that would equal 1/2 times change in concentration of ammonia over time. Okay, so that's a generic. So if I gave you, for example, a number and said the rate at which nitrogen decreases is 20, whatever, units, what would the rate with respect to hydrogen be? So continuing with the math here, so if I'm trying to find the rate of change with respect to hydrogen, I want this portion of it. And so I've got to get rid of this 1/3. So how do I do that mathematically? Multiply both sides by 3. And so what that tells you then, if the rate of disappearance of nitrogen is 20 molarity per second, then the rate with respect to hydrogen over time is 60. Okay, 3 times whatever it was for nitrogen. Now, it's probably easier for you at this point to simply look at the balanced reaction and get that math, but that's not always going to be the case. So here's one to practice with on the next slide. Okay, so this is a lot more complicated. So I'm going to introduce it, then I think you should turn off the video and see if you can work it out. So here's kind of a complex equation. And they give you the rate with respect to permanganate ion, and they say that it disappears with a rate of 2.2 times 10 to the minus 3 molarity per second. And so what is the rate of the reaction? So that's assuming, when it just says rate of reaction, doesn't give you with respect to anything. It's just kind of like assuming there's a coefficient of 1. So the first thing you need to do is you need to say, okay, the rate of this reaction, and put it in terms of all of the reactants and all the products. So I'll get you started. So take the coefficient, it's 1 over the coefficient times the change in concentration of that substance over the change in time. Okay, it's a reactant, so there's a minus sign. And continue and write it with respect to all the rest of them. And then what you're trying to solve for is this rate value. So this tells you that the rate, just the raw rate of the reaction, is equal to whatever these 1 over the coefficient is, times the change in concentration of a particular substance over time. So using the information they gave you about the change in concentration of permanganate over time, see if you can solve for the rate of the reaction. That's part A. And then also, knowing the rate of change in concentration of permanganate over time, can you use that information to calculate the change in concentration of H2O2 over time? So you should be able to do that if you write all these relationships. So I would turn off the video, just give it a shot even if you're kind of lost, and then I'll explain it on the next page. Alrighty, so if you write the rate of the reaction with respect to MnO4, permanganate ion, you get that. Permanganate has a 2 as a coefficient, which is where this denominator or fraction comes from. And you were given the rate of change of concentration of permanganate over time in the problem, okay? And so now remember, it's asking you to solve for just the raw rate, okay? So this expression tells you that you take the change in concentration of permanganate over time and you multiply it by 1/2. So the rate of the reaction itself is half of what was given for permanganate. As far as calculating the reaction rate with respect to another substance in the reaction, before you look down here, I want to present a different look at it. So if you were writing the general rate equation, it would look something like this. With respect to permanganate, and then if you did it with respect to hydrogen peroxide, you would say that equals hydrogen peroxide is a reactant also, and it has a coefficient of 5. Okay, so this might be a typical problem that you would see, okay? And if you simplified this expression without any numbers, and just to compare permanganate with hydrogen peroxide, you would get, okay, change in concentration of hydrogen peroxide over time is, now if I multiply both sides by 5, okay, so that I can just get it in terms of hydrogen peroxide, which is what the question is asking for, okay. So multiply both sides by 5, that would give me 5/2, right? Whatever the value was for the change in permanganate ion. So it's just simple algebra, okay? All right, so plugging in, so we've got 5/2. The change in concentration of permanganate over time that they gave us was 0.0022. All right, and so if you do that math, you get that the rate with respect to hydrogen peroxide, 0.0055. All right. So now that I kind of just wanted you to see it from scratch up there, but now go ahead and look here. Whatever way is easier for you to visualize. Um, the bottom is kind of a shortcut, but it's only if you understand it, okay? So we just established the basic rate of the reaction from part A, and now we're going to write the generic expression for disappearance of hydrogen peroxide. Okay? And again, if we want it just in terms of hydrogen peroxide, we've got to get rid of this 1/5. So we're going to multiply both sides by 5. Right? And we come up with the same answer. So this is pretty simple, but it tends to confuse students. And I probably haven't explained it as clearly as I could. So if you didn't follow me, make a note to, either look in your text or, spend some time learning it. It is important. All right, so we're almost done with this first lecture. This is just kind of simple concept stuff. What are the factors that can affect a reaction rate? Well, the biggie is reactant concentration, okay? So the higher the concentration, the faster the reaction. And you'll learn toward the end of the chapter there's something called the collision theory, that in order for reactants to react and for a reaction to proceed, reactants must collide with each other. And so obviously the more congested or concentrated they are, the more collisions you're going to have and the faster the reaction. Now gases, um, the pressure of a gas is directly proportional to the concentration of gas. So if you're talking about gases, if the pressure goes up, that means